spans eons and encompasses some of the most profound mysteries of all existence. Approximately 13.8 billion years ago, our universe began with an event known as the Big Bang. This was not an explosion in space, but rather an expansion of space itself from an infinitely small, hot, and dense state. In the first few fractions of a second, the universe underwent a period of rapid inflation, expanding exponentially and smoothing out any irregularities. During the first second after the Big Bang, the universe was an incredibly hot and dense plasma of fundamental particles, quarks, gluons, electrons, neutrinos, and photons. As the universe expanded, it began to cool. By the time it was a few microseconds old, quarks started to combine to form protons and neutrons in a process known as baryogenesis. After about 1 second, the universe had cooled sufficiently for these particles to remain stable. Neutrinos decoupled from the rest of the matter, and the universe continued to expand and cool down. As the universe approached about the 3-minute mark, temperatures dropped to around 1 billion degrees Kelvin. This cooling allowed protons and neutrons to come together to form the first atomic nuclei in a process called nucleosynthesis. The primary products of this era were the light elements, specifically hydrogen, helium, and trace amounts of lithium and beryllium. The vast majority of the universe's matter was converted into hydrogen, about 75%, and helium, roughly 25%, with, again, minute amounts of other light elements. This era of nucleosynthesis lasted for only a few minutes, but it set the stage for the chemical composition of the entire universe. Following nucleosynthesis, the universe entered a period known as the cosmic dark ages. During this time, the universe continued to expand and cool, but no new light was produced because the first stars had not formed yet. Around 380,000 years after the Big Bang, the universe had cooled to about 3,000 degrees Kelvin, allowing electrons to combine with protons and form neutral hydrogen atoms. This process, called recombination, made the universe transparent to radiation. The photons released during recombination have traveled through space ever since, forming what we observe today as the cosmic microwave background radiation, or CMB radiation, a faint glow that provides a snapshot of the early universe. With the universe now transparent, gravity began to take over. Tiny fluctuations in the density of matter, remnants of quantum fluctuations during inflation, provided the seeds for the formation of the first stars and galaxies. Roughly 200 million years after the Big Bang, the first stars, known as population 3 stars, began to form. These stars were composed almost entirely of hydrogen and helium, as heavier elements hadn't yet been created. The intense pressure and temperature in their cores allowed nuclear fusion to occur, producing heavier elements and releasing enormous amounts of energy. As more stars formed, they began to group together under the influence of gravity, forming the first galaxies. These shapes and sizes we observe today, including spiral, elliptical, and irregular galaxies. As galaxies formed and evolved, so too did the large-scale structure of the universe. Clusters and superclusters of galaxies emerged, connected by vast filaments of dark matter with enormous voids in between them. Dark matter, an invisible form of matter that does not interact with light, plays a crucial role in the formation and evolution of cosmic structures. Its gravitational influence helps to hold galaxies together and guides their movement. In addition to dark matter, the universe is also influenced by dark energy, a mysterious force that is driving the accelerated expansion of the universe. Discovered in the late 20th century through observations of a distant supernova, dark energy makes up about 68% of the total energy content of the universe, with dark matter comprising about 27% and ordinary matter making up only about 5%. As we look to the future, several possible scenarios for the ultimate fate of the universe have been proposed, each depending on the nature of dark energy and the overall geometry of the universe. The most widely accepted scenario is the Big Freeze, also known as the heat death of the universe. In this scenario, the universe continues to expand forever, driven by dark energy. Over time, galaxies will move further and further apart, stars will burn out, and the universe will become increasingly cold and dark. Eventually, all matter will decay into fundamental particles, and the universe will reach a state of maximum entropy where no more useful energy can be extracted. Another possibility is the Big Crunch. If dark energy were to reverse its effects, or if the density of the universe were higher than currently believed, the expansion could eventually slow and reverse. In this scenario, the universe would begin to contract, with galaxies, stars, and eventually all matter collapsing back into a hot, dense state similar to the conditions of the Big Bang. This could potentially lead to a new Big Bang and a cyclic model of the universe. A more speculative scenario is the Big